So as always, I'll wait until 6:02 to start. Oh, does anyone have any questions before we start?
About the homework, not like material wise.
Mhm.
I just wanted to make sure, like I submitted on Blackboard and it was like you said you wanted a PDF, like a scan of it.
Yes,
Okay.
that can be produced with your phone.
Yeah, no, I did it. I just wanted to make sure
Right.
because at first I thought I accidentally submitted one, like it was just a picture, but I saved it as a PDF form, but then like I scanned it in.
So long as it's a single file and in PDF format and readable, that's what I'm
Okay.
looking for. By the way, I should mention, remember my promise at the beginning of the course, which is this course will be substantially curved. What I said verbatim is curved to the stratosphere. Which means that I expect the average on this assignment to be around 50%. Although I have no idea what it's going to end up being. Actual, we'll see. But in other words, 50% is a pretty good grade. And it's going to be curved up substantially. I am not going to destroy anyone's GPA. But I will be very tough on the assignment grading. And this is because I want to push everyone to produce the best work that they possibly can. So expect tough grading otherwise. Pre-curve. So if you tried and you put a bunch of effort into the homework, then I'm going to be happy about that. Any questions about this specifically?
When will we be getting the answers for the homework?
I am going to upload them within 24 hours from now. So good point. Answers uploaded in 24 hours. Some people emailed me with specific reasons that, so I am willing to grant 24-hour extensions to people who email me in advance. which is why and they have to have a reason. But as a result of this, but I don't give extensions. As in this semester, I'm not going to give any extensions that are longer than 24 hours. So 24 hours from the deadline, I'm posting the homework, and that's that. This the answers. And then you're going to be able to see what I wanted written on these assignments. And then 1 second. For subsequent assignments, you should try and mirror my solutions, mirror the style of my solutions. Any more questions?
Just one quick question. I know you said there was a whole issue like with someone grading the assignments, but there's no rush at all. But I just wanted to know, like, when would the
okay, yes. Grading by the end of the week.
Okay, thanks.
Oh, and I of course I need to tell you one more thing. So last time I uploaded the assignment before the Tuesday lecture. And had I done the Tuesday lecture before uploading the assignment, I would have made modifications to that assignment. So this week I decided to learn from that, and I will upload the assignment after the lecture, depending on how the lecture goes. So the assignment will be up by midnight tonight. Homework 2 will be up by midnight. And further to this, the notes will also be posted. I am a bit behind on the notes. So I have several pages written, but then I have also handwritten pages, and I'm going to convert the handwritten pages into typed up pages. Notes will be posted soon. And probably updated at a later date. So those are the other 2 things that I wanted to mention. And then homework 2 is also going to be due on Tuesday. Okay. Is that all for the preamble on to calculus? Okay, so today I am going to do a tiny bit of theory. And then lots of calculation. And so let's get through the theory section first. Remember, at the end of the last lecture, we defined integration. And what was our definition of integration? The one that we settled on in lectures, which isn't reflected in the notes. We defined the integral from a to b of f of x dx to equal k when there exists a sequence of partitions one second, my writing position is pretty bad. Let me change that a bit. Partitions P sub n of AB such that these upper and lower sums converge to a number, and that number being k. So this is the definition of integration. Now, there comes a question of which functions are integrable. So for example, we showed in class that f of x equals x squared was integrable on the unit interval. And let me also just do this so that I don't have to worry about it for the rest of class. And on the homework, we considered the function f of x is 0 when x is less than 1/2, and 1 when x is greater than or equal to 1/2. And we can draw the graph of this function like this. So let's just restrict the domain to the unit interval. And this function was also integrable, as you showed. And this function is not continuous. So there are some functions which can be somewhat bad, but which are still integrable. Now consider, and I got to this example at the end of the last class, the following function, but consider the function f of x is equal to, it's either 0 or 1, and it's 0 when x is a rational number, and 1 when x is not a rational number. And this function is impossible to graph. And the issue with this function is that if we have any interval xi comma xi plus 1 has xi is strictly less than xi plus 1, so it's an interval of some positive length, then this interval has both rational and irrational numbers. So as a result, all of the upper sums. So if P is any partition of the unit interval, all of the upper rectangles have height 1. Which says that the upper sum of f on any partition is 1. And similarly, the lower sum of f on any partition is 0, because all of the lower rectangles have height 0. Why? Because in any interval, f takes on 2 values. It takes on the value 0 and it takes on the value 1 if the interval has positive length. And so we have a sum of rectangles dividing the base of length 1, and the uppercase, all of their heights are 1. In the lowercase, all of their heights are 0. So the areas that we get are either 1 or 0, and that does not depend on the partition. This holds for any partition. And there's no hope of bringing these numbers together. So f is not integrable. Any questions about that example? Okay, so then what is integrable? And I'm just going to tell you the results. Suppose, well, not, so, okay, what are some sufficient conditions for a function to be integrable?
Does it have to be continuous?
It does not have to be continuous because we saw that this function right here, which is not continuous, is integrable. However, the results that I'm about to mention is that all continuous functions are integrable. So you're right in that we have a result. If f is continuous, so for continuous, I'll abbreviate it to just CTS on an interval. Then f is integrable on AB. And I won't be proving this. So we're just going to take this on faith. So that's good. Every single continuous function defined on a closed interval is integrable. The key point is that the function has to be defined on the whole interval. By the way, notice I'm just going to make a remark. If f is continuous on AB, then by the extreme value theorem, f is bounded on AB. And the extreme value theorem literally just says this. If you have a function that's continuous on an interval, then it's bounded. In fact, we only defined integration for bounded functions. So this is more of a sanity check. We only integrate bounded functions. And when I say we only integrate bounded functions, I should qualify for now. At the end of the course, we're going to talk about what are called improper integrals. And that's a separate notion. Right. So this is a good result. This says that if a function is continuous, we don't have to worry about it. On the assignments, I asked you to show that functions were integrable. And now you couldn't say that the function was continuous and therefore it's integrable. That would not have been enough for the assignments. But now that this assignment is passed, I'm just going to give you this result. And it's a great result, right? So this is the theoretical part number 1. This is just reassurance. Right now, all that I've said this lecture is that continuous functions are integrable. Let's go on to the next part of the theory. And this is the most important theorem. This is called the fundamental theorem of calculus. And this theorem has two parts. And today we're going to discuss part one. And then part two will be saved for the next chapter of the notes, probably at the beginning of next week. Or maybe even later than maybe the second lecture of next week. But before I state what the theorem is, I want to do a small recap of the most important. So FTC part one is the most important theorem in Calc B. Which brings us to a question, but first, let's review the most important theorem in Calc A. And what is the most important theorem of calculus A? Anyone? So what's the most powerful result that you learned in calculus A? Any guesses?
Pythagorean theorem.
Not technically a part of calculus A, and its use comes up in some trig integral, in some trig derivatives, but not necessarily the most useful. No.
Would it be the derivative? The definition of a derivative?
That's a definition. That's not a result. I guess that's a very important thing. Arguably more important, but this is a result. This is a theoretical result that says something. And I'm going to give you a hint. It's not chain or product rule. Chain and product rule are also important, but let's see. Yes. Okay. Someone said it in the comments. The person who said it in the comments is right. The most important theorem is the mean value theorem. Now you may be wondering, really, is the mean value theorem the most important theorem in Calc A? Your experience might not say that it's the most important theorem, but I assure you that it is by far the most important theorem that you learned in that course. So this is an incredibly overpowered theorem. It basically every single proof in calculus uses the mean value theorem. I mean of half of the theorems. This is a ridiculously powerful theorem. So what does this mean value theorem say? The mean value theorem says, suppose I have to make my colors diverse or else it's just all going to be monotone red. Suppose f is a function, is defined on an interval AB. And f is continuous on this interval. And also it's differentiable on the open interval. So in general, we don't have to assume that it's differentiable at the endpoints, although that looks like a minor point. So then what do we have? Then there exists some C in the open interval such that, and does anyone remember what the conclusion is? Anyone? The conclusion of the theorem such that what? No, well, that's not true. F of A does not have to equal F of B. F of A equals F of B is a very specific statement, and that's not generally true. The conclusion is that F prime of C is equal to F of B minus F of A divided by B minus A. So what this looks like is this. Suppose this is your graph, and suppose this is your function right here. Then suppose that I take A and B here. So this is F of A, this is F of B. Then let's say I draw this line segment from A to B. This is, I wanted to do that in a different color. Then what the mean value theorem says is that there exists some point C such that the slope of the function is exactly the difference quotient from F of A to F of B. So this would be our C in the example of the theorem. And you may say, well, okay, that doesn't look that interesting. Why am I saying that this is the most powerful theorem? This looks like an accidental fact. It doesn't look that interesting, but trust me, it is definitely an incredibly overpowered fact. One other way to restate the conclusion is to say that F of B is equal to F of A plus F prime of C times B minus A. So what that tells you is that if you start at the point A comma F of A, and then you do a linear approximation with slope F prime of C, then you're going to exactly correctly calculate the point F of B. So what's slope? Well, the slope is going to be exactly some point F prime of C. So this linear approximation gives the right answer. Correctly calculates F of B. And so that's one of the statements. Okay, so now that we've reviewed the most overpowered theorem in calculus A, let's do the most important theorem in calculus B. So on to FGC part 1. By the way, does anyone have any questions about the statements of the mean value theorem? So I know for a fact that if you've taken calculus A, you've heard of the mean value theorem. It's illegal. It is actually illegal, I think, under the Geneva Convention for Human Rights, to teach a calculus A class and not mention the mean value theorem. It is a very important theorem. Okay, so let's go get on to the fundamental theorem of calculus part 1. And this is an absolutely amazing theorem. You're going to see that this theorem is also very overpowered. Now, before this, I'm going to make a remark. So first, a remark. Suppose that f is integrable. On the closed interval, AB. And that k is some value such that for any partition P, we have that k is sandwiched between the upper and the lower sums. So what can you say about the number k in this case? Well, any guesses?
Then integral.
Then k is what? K is equal to what? Well, k is equal to the integral from a to b of f of x dx. So one way to show that the value k is equal to the integral is to show that it lies between any lower and upper sum. Why? Because if we have a sequence of partitions such that the limits of the lower sums converges to the limits of the upper sums, which we have by the assumption that f is integrable, then since L each LFP sub n is less than or equal to k, we have that their limits is less than or equal to k. And similarly, if we look at any of the upper sums, then k is a lower bound for them. So their k is less than or equal to the limit of the upper sums. But if you have upper sums and lower sums closing in on a number, and then you have some number that's between every single upper and lower sum, then the upper sums and the lower sums have to close in on k, right? Does that make sense? So this says we can show that the integral from a to b of f of x dx is equal to k by showing that every single lower sum of f is less than or equal to k is less than or equal to any upper sum for all p. So that's a commons. Okay, now let's get to the theorem. So here's the main results. suppose that f is integrable, f is integrable on AB, and that f is a function such that f is continuous on the closed interval, and such that the derivative of f is equal to f on the open interval. Then the integral from a to b of f of x dx is equal to f of b minus f of a. So this is the statement of the theorem. What this theorem says is that we can calculate any integral if we have such an f. So this says that if we can find a continuous f such that f prime is equal to f, then we've found the value of the integral. And this is an amazing result. So I'm going to give you an example of how to use this result. And questions about the statement first? Okay, so let's do an example. Let's consider f of x, let's n be any natural number. And consider f of x is equal to x to the n. Can anyone think of a function f whose derivative is x to the n? So I want someone to unmute themselves and tell me a function such whose derivative is x to the n.
So maybe x to the n plus 1 over n plus 1.
Good. Then consider this function right here. Notice that by power rule, f prime of x is equal to n plus 1, x to the n divided by n plus 1 is equal to x to the n. Therefore, by ftc1 the integral from 0 to 1 of x to the n dx is equal to 1 is equal to, well, let's say f of 1 minus f of 0 is equal to 1 to the n plus 1 over n plus 1 minus 0 divided by n plus 1. And that's just 1 over n plus 1. So now all of you should be amazed because in the last lecture, in order to calculate x squared or x cubed as on the homework, you had to bust out formulas for sum of cubes. But here, you don't have to bust out any formulas for sum of cubes. You just notice that the function f has its derivative as x to the n, little f, and therefore you just know what the integral is by this theorem. So this is an incredibly powerful theorem. So look at this solution. It took a lot of work to do integral x squared. Doing the integral from 0 to 1 of x squared dx using Riemann sums was hard. Now we did it in 2 lines. Or this is really like a 1-line solution. And because this is the most important theorem in Calculus B, I'm going to prove it. And in fact, the proof is very short, and the proof directly follows by the mean value theorem. So before we get into the proof, it's important that everyone here understand the statement of the theorem. So are there any questions about the statement or this example? So I'll leave this on the screen and I'll give you 20 seconds to think.
So I just had a question about
Mhm.
the capital F in that first part that you explained. I know it's a function and it's continuous on the interval, but what does it mean, for example, like if we're applying it? Is that what we just found by writing the equation for x to the n? Is it supposed to be, I guess, how would you find it if you're applying this?
Well, the main hypothesis isn't that it's continuous, but that its derivative is f. The derivative of capital F is f, right?
Okay.
Now, so the question is, how do I find such a function, right? Is that your question?
Yeah.
Well, that's literally this course. This entire course is about how to find f. Spoiler, well, actually, I guess this is a twist. This course is literally about finding capital F.
Okay, I think I misunderstood at first. So that's just, yeah, okay, that's just the integral.
Yes. So the entire point of this course is calculational methods for finding f. That's the main problem in this course.
Mm-hmm. So f of b and f of a, you can find that just by looking at the endpoints of the interval.
So this is just the value of capital F on A and B. So you just evaluate it, right?
Mm-hmm.
So for example, let's look at the function here. F of x to the n plus 1 divided by n plus 1. What is f of 1? So if f of x is this, then f of 1 is, go ahead.
Just what you circled?
Yeah, 1 to the n plus 1 over divided by n plus 1. And that's just 1 over n plus 1. And then f of 0 is just 0 divided by n plus 1, which is 0. So if you found a function whose derivative is little f, then you just evaluate the function at the endpoints and you have the integral.
Okay. Yeah, I think I just needed it re-explained a second time. That makes more sense.
Thanks for asking. It's important that you ask because several other people have this question. So with this new piece of information that this entire course is actually about strategies for finding capital F, and that this results is the central results in the entire class, you are going to spend so much time finding capital F. This is the main computational problem. And so it's important that we really understand this results. So by the way, if a function is differentiable, then it's continuous. So the function f automatically has to be continuous on the open interval. So the fact that f is continuous on the closed interval, the only additional pieces of information that this provides are that f is continuous at the endpoints. So this hypothesis is a pretty weak hypothesis. The much stronger hypothesis is this one. If you, so in this class, we're going to just assume that a lot of functions are continuous. On the homework, I asked you to show that one function was continuous carefully. When applying this theorem, you're not going to have to justify the continuity. You're just going to have to justify that you found a function f as such. And by the way, that brings me to a definition. A continuous f such that f prime is equal to f is called an antiderivative of little f. So we're going to be using this word very frequently, the notion of an antiderivative. And so FTC1 says that if we can find an antiderivative of f, then we know the integral. So in other words, the problem of integration is reduced to the problem of finding antiderivative. Then you may ask, well, do antiderivatives exist in general? And the answer is no, antiderivatives do not exist in general. In other words, it is not the case that every single differentiable function, and not every integrable function has an antiderivative. But FTC part 2 will say that this happens in most cases. Specifically for continuous functions. It'll say a bit more, but this will be saved for later. So FTC2 will tell us that the strategy of trying to find an antiderivative is a strategy that will work for computing the integral of the function whenever you have a continuous function. It'll say something stronger than that, but that will be the main moral lesson. But we're not discussing part 2 right now. We're discussing part 1 right now. And part 1 says that if I have a function f that's integrable and I have an antiderivative, then bam, I know what the integral is. So let's do the proof of this theorem. It is a very short proof and it is a very elegant proof. And so this is the last theoretical thing that we're doing for today, and then the rest of it is going to be practical. So bear with me for this single argument. So what we're going to do is suppose that little f and capital F are as hypothesized in the theorem. So f is integrable. Capital F is continuous. And f prime is equal to f on the open interval. What we're going to do is do the strategy that I discussed before the theorem. We will show that for any partition P, that we have that the lower sum of f on P is less than or equal to f of B minus f of A is less than or equal to the upper sum of f on P. So remember that the claim in the theorem is that the integral is equal to f of B minus f of A. And so to show that the integral is this, we can show that for any partition P, the upper and the lower sums lie, f of B minus f of A lies between the lower and the upper sums. So that will suffice. Well, to this end, suppose that P be the partition x naught is less than x1 is less than ... is less than xn. So let's suppose that we have some points in the partition. Then what we're going to do is consider the expression f of B minus f of A. So we are going to write this as f of xn, which is equal to B, remember? X naught is equal to A, f of xn minus f of xn minus 1 plus f of xn minus 1 minus f of xn minus 2, and so on until we reach f of x1 minus f of x naught. Now, why does this identity holds? Can anyone tell me?
Can you repeat the question, please?
So I've considered f of B minus f of A, and then I've rewritten it as f of xn minus f of xn minus 1 plus f of xn minus 1 minus f of xn minus 2, plus and so on until I got to fx1 minus fx naught. And I claim that this is equal to this. Why are these two things equal? Does that make sense? So x naught to xn were the endpoints of this partition. X naught is equal to a, xn is equal to b. So originally I had xn minus x naught. But now I claim that I can throw in all of these terms and I get something that's equal to this. Why can I do that?
This might be totally wrong, but is it because you can, it's basically like looking at one large partition, you're looking at both ends, and that's why they're equal, because each smaller partition technically makes up the interval? Or was that?
Well, yeah, so what's true is that you might be onto something. If we look at this interval right here, let's say this is A and this is B, and this is x1, and this is xn minus 1, right? So then there are a bunch of points, right? Then what I've done is I've considered the difference of f between this endpoint here and this endpoint here. So for each interval, I've considered f of the upper endpoint minus f of the lower endpoint. Right? Does that make sense? But why are these things equal? Okay, so I'll tell you the answer. Well, look at a small example. Let's suppose P is equal to x naught less than x1 less than x2, right? So this is a small example. Then f of b minus f of a is equal to, first off, f of x2 minus f of x naught by definition, because x naught is equal to a, x naught is equal to a, and x2 is equal to b, right? Because it's a partition of this interval. And then I wrote this as f of x2 minus f of x1 plus f of x1 minus f of x naught. And why are these two things equal? So does this equality hold? Anyone?
Yes.
Why? I mean, it's a pretty straightforward question. Why is this equal to this? Don't overthink it.
Because f of x of 1 is negative in one, positive in the other.
Yes, so these two cancel out, right? Well, look at the general case. This one cancels with this one, right? Then this one cancels with the next one. And what's left over once you've performed all of these cancellations? What's left over is just the endpoints, right? So you'll always have this cancellation. So this is called a telescoping sum.
Which one did you cancel?
So in general, I can write this. I can write it as the sum from I is equal to 1 to n of f of x I minus f of xi minus 1. Then if I look at two consecutive terms, the first term has a negative term, and the next one has a positive term, and the negative term and the positive term exactly cancel out. Right? Does that make sense?
Yeah.
And so you have all of these cancellations occurring in pairs. And this is called telescoping sum. So I can write f of b minus a like this. This is called a telescoping sum. It's a trick. Okay, now by the mean value theorem, let me plug in my laptop. There is some. Let's call it T of I between xi minus 1 and xi, such that we're going to write f of xi minus f of xi minus 1 as what's the derivative of capital F? It's little f, right? By hypothesis. And this is because capital F prime is equal to F, right? So the mean value theorem tells me that for each one of these differences of endpoints, I can look at the derivative of capital F at some point t sub I between the two endpoints. And then the difference is exactly given by this slope multiplied by this displacement. Does that make sense? Any questions? So what that says is that f of b minus f of a is equal to the sum from I is equal to 0 to n of xi minus 1, xi minus x sub I minus 1 times f of t sub I, right? But now let's consider the upper sum of f on p. This is equal to the sum from I is equal to 0 to n of x sub I minus x sub I minus 1 times the supremum on this interval of the function f. And let's look at the lower sum. This is equal to the sum from I is equal to 0 to n of x sub I minus x sub I minus 1 times the infimum on this interval of the function f. And can anyone tell me why f is sandwiched between the upper sum and the lower sum?
Does it have something to do with it being continuous throughout these values?
So at this point, we used that f was continuous elsewhere. We used it when we applied the mean value theorem, right? So the assumption of continuity came into when we applied the mean value theorem. I could actually derive this inequality, this bound, if I just had these three expressions. I do not need to use continuity in order to conclude that one is between the other, that I have bounds. So continuity does not come into play in this step. Any other guesses? what is the definition of the infimum of a function on this interval?
It'd be the lowest.
Right, so if the function attains its lowest value, if it does, then it's the lowest value that the function f takes on this interval, right? Actually, we know that f is continuous. So if we know that, actually, no, we don't know that f is continuous, never mind. If we knew that f was continuous, we could replace this with minimum. And we could replace this with maximum, right? Well, what is f of t sub I? F of t sub I is what? So here we have the minimum value, here we have the maximum value, and what do we have here? Well, f of t sub I is some value that the function has, right? So the lowest value that the function takes is less than or equal to some value that the function takes, right? Does that make sense? And that's less than or equal to the biggest value that the function takes. Isn't that right?
I'm sorry, can
So-
you repeat that again?
The infimum is the greatest lower bound of all of the values that f takes on this interval. So suppose that f attains a minimum value on this interval. Then the infimum is the lowest possible value that f takes, right? Do you agree?
Yes.
And what's the supremum? If f attains its supremum, then supremum of f is the biggest value that f takes on this interval, right?
Yeah.
But f of t sub I is just some value that f takes on this interval.
Okay.
So it is by definition bounded between the lowest and the biggest values that f takes on this interval. So what was this proof so far? We wanted to show that f of b minus f of a was between the lower sum and the upper sum over any partition. So we took some partition, then we wrote a telescoping sum like this. Then for every single difference between endpoints of f, we applied the mean value theorem to f to write it as f of p sub I. Then we wrote out what this expression was, and then we wrote out what the upper sum and the lower sum was. And for every single one of these terms, we have a bound like this. So LFP is less than or equal to f of b minus f of a is less than or equal to the upper sum of f of p. Therefore, the integral from a to b of f of x dx is equal to f of b minus f of a. End of proof. Didn't I tell you that the mean value theorem was completely overpowered? So just by writing this difference in a clever telescoping way and using the mean value theorem, we immediately are able to integrate functions of which we have an antiderivative. So that is all the theory that I'm going to do. And you're not going to be asked questions about this proof, but I wanted to show you this proof because it shows how overpowered the mean value theorem is. And also because it is the most important theorem in this course. The basis of absolutely everything that we'll do for the rest of the semester is the statement of the theorem. The fact that we are able to find integrals if we know an antiderivative, right? So we're all clear on the statement, right? And then here's the proof. And just to review the steps of the proof again, we made some remarks before the proof that if f of b minus f of a was sandwiched between every single lower sum and every single upper sum, and we knew that the function f was integrable, which we assumed, then we know for a fact that f of b minus f of a is equal to the integral of the function. So we're going to show this inequality. Well, then to this end, we take some partition. We write f of b minus f of a in this telescoping manner. We apply the mean value theorem to each difference, and then we just compare them, and we're done. That's the entire proof. So it requires two very clever ideas. The two really clever ideas are to write it as a telescoping sum and to apply the mean value theorem. But once you have those two ideas, just those two sentences, you have the entire proof. And now you're able to justify, we've completely, fully, rigorously justified that the integral of x to the n for any natural number is 1 over n plus 1. So we have done every single example of power functions. Well, for the natural numbers, it doesn't have to be a natural number. It can also be a real number. We'll get to that in a second. But look at how much work we had to do. Well, the mean value theorem and this telescoping idea, bam, all of the work is done for us. Isn't that amazing? Okay, so what's the main lesson? The main lesson is that there is a notion of an antiderivative. If we have a function f, then a function whose derivative is little f is called an antiderivative of f. And the mean value theorem, the fundamental theorem of calculus part 1 says that if we have an antiderivative, then we know the integral. The integral is just f of b minus f of a. Right? So that much should be clear because I've said it over and over again. Okay, now the rest of this course is going to be about how to find antiderivatives. And now I'm going to move on to that. No questions? Okay, I think we should have a break. So it's been an hour and 15 minutes. Let's take a break until, I'm going to try and do 2 breaks today. So let's take a break until 7:25. So break until 7:25. And then if you have any questions after the break, if you think of any during the break, you can ask me. So I will zoom out and I will display the entire proof on the screen. There. Did anyone find that proof elegant or appreciate it? Sadness, no responses. Okay, see you at 7:25. Okay. Does anyone have any questions? Did they think of any questions during the break? Okay, I'm going to resume. So first off, let's take an inventory of calculus A. Of differentiation. So can anyone tell me in one paragraph absolutely everything that you learned about differentiation in calculus A? I mean, you all are expected to have taken calculus A. So what did you learn in that course? Let's list it.
Ways to get the derivative.
Yes, what ways were those?
Power rule quotient,
Okay, you had power rule,
chain rule.
chain rule. I'm not going to write down quotient rule because quotient rule follows from chain rule. What else? Related rates is a type of problem, not a type of derivative. That's not something about that's about word problems. Well, what about actual differentiation? Continue. Let's continue. There are some other things. So are you telling me that the only thing that you learned in calculus A is power rule, chain rule, and quotient rule about taking derivatives? Is that it?
I guess product rule too. if that
Yes,
counts.
product rule is one of them. Now, power rule says how to differentiate that x to the r prime is equal to r x to the r minus 1. Right? So this says how to differentiate power functions. What are some other functions that we learned the derivatives of? What are some functions that you know how to differentiate that we learned the derivatives of? Okay, trig functions. And the trig functions in our arsenal are sine, cosine, tangents. So 1 over sine is cosecant, secant, and cotangent. And then I'm going to include as a separate category inverse trig functions. And those are, what are my, well, I'll tell you what the important ones are. The important ones are arcsine and arctan. Okay, what else did you learn how to differentiate?
Oh, logs.
Yes. And what's related to logarithms?
Oh,
And one
natural
more thing.
logs.
Well, natural logs are logs. Logs and what? What is the inverse function of the logarithm?
E.
Exponential. So logarithms and exponentials. So actually, I'm going to take what I wrote power rule right here, and I'm going to erase it from here. And I'm going to put it downstairs. Power, x to the r, power functions. There are also technically some other results that you know. You know also the facts that if you multiply a function by a constant and take its derivative, then what is this equal to?
The derivative, I mean, the constant is just on the outside.
So you can say it's the constant multiple of the derivative, right? And now what if I take the derivative of a sum of functions?
It's the sum of the derivatives.
Exactly. I am going to claim that what we've written right here is everything that you know about differentiation. About derivatives in Calc A. And one way that I can organize all of this material is I can say the following. So in essence, we have some basic functions. And those functions are, e.g. power functions, trig, exponentials and logs. And we know their derivatives. And we can say that we memorized them. So in calculus A, you essentially memorize them. And then if those derivatives came up on an assignment or an exam, then you just pulled those derivatives out, right? So basically you have some basic functions and you know the derivatives of those basic functions, right? Then the rest of the functions that you consider are built out of basic functions. In three ways. One is bilinear combinations. So in other words, C1F plus C2G. 2 by products of functions by multiplying. We can write f dot g of x is equal to f of x times g of x. Or 3 by composing. So f circle g of x is equal to what?
F of g of x.
Exactly. For products, I'll use a dot, and for compositions, I'll use a circle. I mean, sometimes I won't write the dot. Sometimes I'll just write FG, but it's sometimes clearer if you write the dot. Then the circle means composition. So every single function that you encountered in the course was built out of basic functions using these operations. And then what these rules say is exactly how to differentiate all of the basic functions. And for each way that you can get a function out of basic functions, or which way you can put functions together, how to differentiate them. And so that gives you a complete inventory and a complete algorithm for differentiating functions. You just recognize how the function is built out of basic functions, and then you apply linearity of differentiation. In other words, the fact that derivatives distribute over scaling and addition, and then product and chain rule. And then eventually you get down to the basic functions, and then you just have the basic functions committed to memory, right? So that's how differentiation works. So to give an example, let's consider the function f of x is equal to sine x times x squared plus 5 to the 10th power. Then what is f prime of x? So what rule do I apply first?
Chain rule.
What's the function on the inside and what's the function on the outside?
Inside is x squared plus 5, and then outside is x to the 10.
Well, that's one of the factors, right? So, but that's not the whole function. So we do chain rule second, but first we have to deal with what is this expression at the top level? At the top level, what is it? It's a product of two functions, right? So the first thing that we do is product rule. We have to first deal with the product, and then we have to deal with the composition. What's the derivative of sine? Everyone should be saying this at the same time. What is the derivative of sine?
Cosine.
Yep. And then we leave this untouched. And then we have sine by the derivative of this function, right? And what rule do we apply now?
Chain.
Good. So this is cos x, x squared plus 5 to the 10th power plus sine x. And what does chain rule tell us that the derivative of this is? Again.
Is it 10? Oh, wait, is it 10 times x squared plus 5 to the 9 times 2x?
Yes, good. And then all of this can be rearranged, I guess, if you want to make it nice. You can write cos x x squared plus 5 to the 10th. I could also factor it plus 20x sine x, x squared plus 5 to the 9th. Oops. So I just made this function up right now. But the point is, how is this function built? It's built as a product of two functions. What are the two functions? One of them is sine x. That's a basic function. We know how to differentiate basic functions, right? What is the other function? Well, it's a composition of two functions. So you have to recognize that this is a composition of x to the 10th as the outer function and x squared plus 5 as the inner function, right? And then, well, how do you differentiate the outer function? The outer function, power rule applies, right? Now, what about the inner function? Technically, the inner function is a linear combination. So you technically change it to the derivative of x squared and the derivative of 5. But then power rule applies for x squared, right? So we can see that in this example, we used all of these rules. All of these rules came into play. We sort of implicitly used the linearity rule, but every single one was used in calculating this, right? So this is how differentiation works. Now, here are some common mistakes. So first off, the derivative of f times g is not equal to the derivative of f times the derivative of g, right? That doesn't happen. So this is a very common mistake. You can't distribute derivatives over multiplication like this naively. In fact, the derivative of f times g is equal to f prime times g plus f g prime, right? So this is a common pitfall. You can, while you can take constants out of derivatives and you can take sums out of derivatives, you can't take products out of derivatives. There's an explicit rule about that, right? Okay, I don't think I have any more common mistakes. That's just a common mistake. Now, in this course, we want to undo this process.
I just have a quick question regarding the chain rule process of it. What is the exponent in the second line of the chain rule on the outside of the x squared plus 5 parenthesis?
So that's a 9.
Okay,
and the reason is because in this outer function, we can say let's f of x equal x to the 10th, and g of x is equal to x squared plus 5, right? Then this function right here is f of g of x, right? Do you agree?
Mhm.
And so what's the derivative of x to the 10th? Well, it's just 10 times x to the 9, right?
Okay.
And then let's just, for the sake of completion, write down what product and chain rule are. So product rule, I've written it above, says that f times g prime is equal to f prime times g plus f times g prime. And chain rule says that f composed g prime is equal to f prime composed g times g prime, right? Or to write it in a different way, using variables, using x, I can say that f of x times g of x prime is equal to f prime of x times g of x plus f of x times g prime of x. So now you see why I don't usually write the x. It sort of gets annoying. And f of g of x prime is equal to f prime of g of x times g prime of x, right? But sort of the quick and breezy way to write them is like this. So all of you have seen product and chain rule before, because this is calculus B, and you've learned how to differentiate. And then I'm going to remind you what the derivatives of all of the basic functions are as well. And so all of these are going to correspond to basic tools in our toolbox for integration. But as we're going to see, integration is actually very tricky. Very tricky. Because it's hard to do the process backwards. Is not straightforward. And in general, you have to be very clever. Well, you can give integrals that are hard. This requires a degree of cleverness. And there are going to be a lot of tricks. And you're going to see that it's going to require a bunch of work to learn it. Learning this is hard. Let me just open this window. Okay, so that has been our inventory of calculus A. And now we're all on the same page of what exactly you learned in the first course. And this is exactly what I'm going to assume going into this course. So this is basically everything that you need to know from calculus A. It fits on a single page. Differentiation isn't that hard. You just follow, you recognize. So the key to differentiating any function is to ask the question, what is my function? And this is actually a very profound question. To answer what my function is requires breaking down the function and understanding how it is composed out of the elementary functions using all of these operations that we can do to build compound functions, right? And those operations are in general going to be multiplying, composing, and scaling and adding. And then things like dividing, it follows out of this because 1 over x, 1 over f is 1 over x composed with f. So quotient rule isn't really a basic rule. Quotient rule follows from chain rule. So I don't even think of that quotient rule deserves to be its own theorem. This is the complete inventory. And so there are 6 trig functions. There are 2 inverse trig functions. You may consider, for example, arc cos, but arc cos plus arc sine is equal to what? Does anyone remember their facts about inverse trig functions?
Is it 1?
Well, let's look at a triangle. So suppose it's a right triangle. This is some angle theta. And then suppose this side right here is sine theta, right? And this side right here is cosine theta. Then arc sine, if instead we have 1 square root a, let's say it's like this, then this angle right here is arc sine a. And what is this angle right here? How can I write that angle in terms of
B?
there is, well, let's say there's no B, there's only A.
Just A.
Well, A is this side, it's not the angle. So the angle opposite is arc sine of A, and the angle adjacent to the side is
Arc cosine?
Yes. Now, what is the sum of these two angles in a right triangle? In radians. So first off, what is the sum of the angles in a triangle? What are the sum of the 3 angles in a triangle?
180 degrees.
What about radians? It is
Pi.
yes. Now, what about a right angle? How much is a right angle in radians?
½ pi.
Pi over 2, good. And so what is the sum of the remaining angles?
3/2 pi.
Pi over 2.
Yeah.
Well, pi minus pi over 2. Also, let me plug in my tablets. It is. Whoops. Also complaining about battery life. So in other words, the function arc cos is actually just negative arc sine. So arc cos is just pi over 2 minus arc sine. That's why their arc cos really isn't a function in its own right. You can say that there are only 2 functions. We don't consider arc cosecant, arc secant, or arc cotangent. So you can, as far as this course is concerned, there are only 2 inverse trig functions, right? So there are 6 trig functions, 2 inverse trig functions. Then there's exponentials and logarithms, those are 2 functions. And then you have power functions. So in total, the number of derivatives that you have to memorize is 6, 8, 10, 11. So 11 derivatives that you commit to memory. Then 2 big rules and sort of 1 rule and 2 rules that you use implicitly. That is everything that you learned about differentiation in Calculus A. I'll just highlight everything. Okay, so let's get on to what we are studying. Any questions about this, by the way? Okay, so first off, I'm going to introduce the notion of an indefinite integral. So suppose that f is a function. Suppose that f is a function. And that's capital F is an antiderivative of f. So in other words, capital F prime is equal to F. Then we write that the integral of f of x dx is equal to f of x. So this is without bounds. So in other words, when we omit bounds on the integral, we are referring to something called the indefinite integral, and the indefinite integral of a function is just any antiderivative of that function. This is the indefinite integral. So the indefinite integral just refers to any antiderivative of a function. As I mentioned before, not every single integrable function. There are some discontinuous functions that do not. There are some discontinuous functions that do not have an antiderivative, but that are integrable. So strictly speaking, the indefinite integral is less general than the definite integral, because you might be able to find integrals of some functions on an interval, but you might not be able to find an antiderivative. But when it comes to calculating integrals, if we have an indefinite integral, then we know all of the definite integrals, because we just do that by evaluating this function at 2 different points and taking the difference, right? Okay, so moving on, we're going to use this notation. But let me say one more thing. So here is a small theoretical thing. Notice that if f prime is equal to f and c is a constant, then what's the derivative of f plus c?
F.
As well, because the derivative of any constant is 0. So f plus c is also an antiderivative. Now, conversely, if f prime is equal to g prime is equal to f, then f minus g prime is equal to what? So if f prime is equal to g prime, then f minus g prime is what?
0.
Exactly. And by the mean value theorem, the most overpowered theorem in calculus, we know that f minus g is constant. On an interval. So this is if we consider if the definition is restricted to an interval. If we take 2 disconnected intervals that don't interact, then technically the constants can be different on the 2 different intervals. So that's just a technical point, but I won't go much into that point. By the way, I'm going to do one quick proof with the mean value theorem. Suppose, let's say, suppose h prime is equal to 0 on an interval AB. Then if h of x does not equal to h of y. So if it's not constant for x comma y in AB, then by the mean value theorem, h prime of t is equal to h of y minus h of x divided by y minus x for some at, and this expression does not equal to 0, and that's a contradiction. So in other words, if h prime is 0 on an interval, then the function has to be constant on that interval by the mean value theorem. So most OP theorem. But what does that mean? That means that every single antiderivative of the function f, they're all just given by adding a constant to any antiderivative. So there is this global conspiracy by calculus teachers. That's the only correct thing to write is that the indefinite integral of f of x dx is equal to f plus c. So in other words, you always have to write plus c at the end of your indefinite integrals. So because it's a more general version, it's not just that f is an antiderivative, f plus c is an antiderivative for any constant c. So always write plus c at the ends of indefinite integrals. Why? It's a mean. It's just everyone's agreed that you lose points otherwise. There are lots of jokes in mathematics where the punchline is forgetting to write plus c. So when we write indefinite integrals, we always write plus c at the end. And I call this a global conspiracy, and it's basically that. Calculus teachers have just agreed that we're going to force you to write plus c, and you lose points if you don't write plus c. And this is a thing. It doesn't have to be this way, but it happens to be the case that it is this way. And the reason really is this discussion right here, that if f is an antiderivative, then f plus c is also an antiderivative, and all antiderivatives on a closed interval are related by a constant because of the most overpowered theorem, the mean value theorem. So in other words, always write plus c. Okay, without further ado, let's actually get to how do I find techniques for integration. Okay, the first technique is integration by inspection. So in general, you can find an antiderivative by pulling it out of thin air. So in other words, just claiming that f prime is equal to f. So I can give you one example of this. So what's a particularly terrible example? Okay, so for example, let's consider the function sine to the sixth. Okay, let's actually write down any. No, I don't have to do an example. Let's look at the example that we had above. We had the function sine of x squared plus 5 to the 10th. Then notice that capital F prime is equal to cosine x squared plus 5 to the 10th time plus 20 x sine x times x squared plus 5 to the 9th. So the integral of the indefinite integral of cosine x squared plus 5 to the 10th plus 20 x sine x x squared plus 5 to the 9th power dx is equal to the indefinite integral sine x squared plus 5 to the 10th power. Why? Because you differentiate and you check. So this is the trick known as pulling it out of thin air, right? I've just pulled an antiderivative out of thin air. Now I did this by differentiating the function and saying what function I was going to integrate. But let's say I started with this function. How would I know that this function is its antiderivative? Why? How would I think about this? So this in general violates the show your work principle. And in other words, often this will not get you credits, but it works. So use this will not get you credits. But it works. Theoretically, right? In other words, you can pull an antiderivative out of thin air. If somehow you manage to do it, then you can just verify that it's an antiderivative by differentiating. However, there are some basic integrals that you have to memorize. Just as there are basic functions. And in fact, all of those, these are in particular exactly those that correspond to derivatives of basic functions. To the 11 derivatives we counted above of basic functions. So what are our basic functions? So first off, we have power rule. We have that's x to the r prime. Whoops, is equal to r times x to the r minus 1. So we get a basic integral rule from this. And that says that the integral of x to the r dx is equal to x to the r plus 1 divided by r plus 1 plus c for there's one value for which this does not work. What value does it not work for? So for one value, I get division by 0. Which value does it not work for?
-1.
Yes, so we have to exclude the case r is equal to -1. But when it comes to -1, what's the derivative of the logarithm of x? What's the derivative of log x? Not everyone at the same time. We know how to differentiate log x. What's the derivative of log x? Come on.
1 over x.
Yeah. So in other words, the antiderivative of 1 over x is what?
Log x.
Yeah. Now except that log is not defined for negative numbers. The domain of log is x is greater than 0. Now let's consider the function, consider log of minus x. What is, so the domain of this is negative numbers. And what's the derivative of this?
Is that just -1 over x?
-1 over, negative x, right?
Yeah.
So that's also equal to 1 over x. So in other words, in general, the domain of the logarithm of the absolute value of x is r less 0, right? And log of absolute value of x prime is equal to 1 over x. So there's actually a more general antiderivative. So more generally, the integral of 1 over x dx is equal to logarithm of the absolute value of x plus c. So this is actually not the most general formula. Not valid for negative x. So this is not the biggest domain. But this formula is more general. So this is the formula that you should actually use. The integral of 1 over x dx is logarithm of the absolute value of x. This applies to antiderivatives whose domain is the negative numbers as well. Because 1 over x, for example, you have to integrate it on an interval that does not include 0, because otherwise the function isn't defined everywhere and it's not bounded. But if you integrate it on a domain of negative numbers, then this formula works. So this is the more general formula. So you have power rule, and then that tells you what the antiderivative is for r does not equal to -1. This tells you what the antiderivative is for r equals -1. Then what about exponentials? What's the derivative of e to the x?
E to the x.
Yeah. So in other words, the antiderivative of e to the x dx is equal to What do I write?
E to the x plus c.
Yes, good. You remember the plus c. I was going to wait for someone to say it without the plus c and then correct them. Okay, now basically, then you have a bunch of trig functions. So here are the trig integrals. And I'm actually not going to write what the derivatives are. I'm just going to write what the antiderivatives are. So I have a table here. Well, you can check that the integral of cosine x is sine x dx. Sorry, no, not dx. Why am I writing dx? Sine x plus c. You can check that the integral of sine x. What should this integral be?
Negative cosine of x plus
Good.
c.
Yes, it's negative because the derivative of cosine is minus sine. So the derivative of negative cosine is sine. Okay, the integral of secant squared is equal to what?
Tan of x secant of x plus c.
No, just tan of x. The derivative of
Oh,
tan of
okay.
x is secant of x, but pretty
Right.
close. Okay, now what about secant tan? Which is, I think, the function that you mentioned. What is this? What is the antiderivative of this?
Is it tan squared of x plus c?
Well, it's going to be one of the 6
Oh.
basic functions, right?
So secant
Yes, secant x
plus
plus
c.
now, what's the derivative of cosecant? It's going to be cosecant x cotangent x dx is equal to cosecant. And then the derivative of tan of cotangent is negative cotangent squared. So we're going to remove the negative sign from the integral. Sorry, not cotangent, cosecant squared. Whoops. This is going to be cotangent, negative cotangent x plus c. So remember, we have 6 basic trig functions. Those basic trig functions have derivatives, and so we get the following formulas. Notice there's an inverse process. You basically have to memorize those. So if you have an integral and you have secant tan, you just have to remember that the derivative of secant is a secant tan. But remember, we have 11 basic functions, so you only have to memorize 11 formulas. Here are 6 of the 11 formulas. How would I know that the integral of cosecant squared is negative cotangent? Just by memory. You have 11 basic functions. You have 11 basic integrals. Okay, now let's do the inverse trig functions. What's the derivative of arctan? Does anyone remember?
Is it 1 over 1 plus x squared?
Good. So the integral of 1 over 1 plus x squared dx is equal to arctan of x plus c. And I honestly think that this integral right here is the most non-trivial integral because 1 over 1 plus x squared, it's a rational function. It lives in the world of quotients of polynomials. What would make you think, unless you remembered this formula, that inverse trig functions come into play, right? This is really non-trivial. Well, why would you think that the antiderivative was arctan? Well, you have to know it from memory. Now, what about arcsine? So arcsine is better than arccos in a way because its derivative does not have a negative sign, whereas arccos is negative, the derivative of this. What's the derivative of arcsine? Does anyone remember?
Is it 1 over the square root of
1
squared.
over square root 1 minus x squared.
Yes, good memory. Yeah. So the integral of 1 over the square roots of 1 minus x squared dx is arcsine plus c. Let's see. Here are 2 of the formulas. So here are 6 of the formulas, and here are 3 of the formulas. So these 11 formulas, power rule, how to integrate a power when that power is not -1. How to integrate that power when the power is -1, that corresponds to the logarithm of the absolute value of x. Remember to always include the absolute value when you integrate 1 over x. The integral of e to the x is e to the x. Then you have these 6 trig integrals, and then you have these 2 inverse trig integrals. So 11 basic integrals. And these are always solved by inspection. By inspection. So in other words, if whenever you're solving an integral, you get down to one of these 11 integrals, then you just say what the answer is. You pull the derivative out of thin air, and you are allowed to do that only in these 11 examples. So this is the complete list of functions that you can integrate by inspection while retaining full credits. And conversely, you actually do need to memorize these formulas. The inverse trig ones are the most non-trivial ones. And then if you just have a product of trig functions, well, you try and remember which one it is. You won't be seeing these 3 formulas as much. These come up a lot. Okay, let me make the page bigger. Whoops, that was a mistake. Hopefully I did not mess anything up. Oh, no, that worked. Okay, good. Okay, so that's integration method 1. This is by inspection. Integration method 2 is linearity of integration. So we know that the derivative of f plus g prime is equal to f prime plus g prime, right? So in other words, suppose, let's actually write it like this. Let's make these be capital F and capital G. And then suppose, okay, f prime is equal to f, g prime is equal to g. Then the antiderivative of f plus g is equal to what? How can I write this just in terms of lowercase f and lowercase g? So remember, sorry, that this formula says that the antiderivative of g is equal to g. And this formula says that the antiderivative of f is capital F, right? So what is the antiderivative of f plus g?
Capital F plus G plus C.
Yes, but we can also write that as the integral of f of x dx plus the integral of g of x dx. Right? And also, the integral of c times f of x dx, where c is a constant, is equal to what should it be in terms of the integral of f of x, the indefinite integral of f of x?
Would it be c, then the integral of f of x dx?
Yep. You had linearity of differentiation and you have linearity of integration. It's important that c is a constant. C must be a constant to apply this. And of course, in general, remember that the integral of f times g of x dx does not equal to the integral of f of x dx times the integral of g of x dx. This is false. So for example, let's consider the integral of x squared dx. Let's consider the integral to go from 0 to 1. What is the antiderivative of x squared from 0 to 1? This was on your, no, we did this in lecture.
1/3.
Yeah. Now, what's the antiderivative from 0? Sorry, not the antiderivative, but the definite integral. By the way, integrals with bounds are called definite integrals. What's the definite integral of x from 0 to 1?
1/2.
Right. So notice that the integral of x from 0 to 1 dx times itself that's 1/4. Or rather, I should write that this is equal to 1/4, and that does not equal to 1/3, which is the integral from 0 to 1 of x squared dx. So in this example, you can see that integration does not distribute over multiplication. In fact, there is no general formula for integrating a product. Which is why integration is hard. And this is a super important point, very important. This is why integration is hard. So NB means important. That's what that abbreviation stands for. Okay, everyone should take 10 seconds to process this. There is no general formula for integrating a product. If you encounter a product, you have to use clever tricks to integrate it. In general, there's nothing that just says what the answer is. Okay, well, so this is linearity of integration. So I'm demonstrating some limits to the linearity of integration. This is not covered by linearity of integration, but if you have sums and constants, then you can integrate it. But a consequence of linearity, we can, for example, integrate any polynomial. So let's say we want to find the indefinite integral of x squared plus 5x plus 2 dx. Then what does linearity tell me?
That it'll be 1/3.
Where there are
Oh.
no bounds. We want antiderivatives.
I'm sorry, integral of x squared dx plus integral of 5x dx plus integral
Let's
of 2.
do 2 steps at once. How can I rewrite the integral of 5x?
Integral of 5x dx.
And how can I simplify that? What's the other rule that I have? I can also take constants out of integrals, right? So I can write that
so
as 5 times the integral of x dx. And then I guess plus 2 times the integral of 1 dx. And then I just won't write the 1. And so then all of these are solved by power rule. So what's the antiderivative of x squared?
1/3.
X cubed divided by 3. Again, no bounds. It's we want a function of x. Then plus 5 x squared over 2, and then plus 2x, and then there's a single constant c. Single constants. At the ends. So we don't introduce a separate constants for each one of these integrals. At the end, we just introduce a constant like this. So as a consequence of linearity, we can integrate any polynomial, right? If we have power rule, then any polynomial, its integral follows from power rule using linearity. Okay, so going back up top, we had Arsenal. This is everything that you knew about differentiation from calculus A. You knew the 11 basic integrals, so we've covered these. Sorry, the 11 basic derivatives, and so you get 11 basic integral rules. You knew linearity of differentiation, and so you get linearity of integration. And then we have remaining product and chain rule, right? So now we're going to see how product and chain rule translate into the world of integration. Now, for the next two sections, we'll see that product rule gives integration by parts. And chain rule gives integration by substitution. So these are going to be two tools in our arsenal for integration. And they're each going to correspond to one of the two other basic rules. And then those are the integration techniques that correspond to everything that you learned in calculus A. Then there are going to be some facts about algebra and functions that are going to tell you how to use these rules in a very clever way. So there are going to be several more techniques. But you should think of all of these as exactly corresponding to tools in your calculus A skill set. So first, I'll discuss substitution. So I've said that this corresponds to chain rule. So if we take G composed, well, let's say F composed G prime of X is equal to. What is the statement of chain rule?
F prime of G of X times G prime of X.
Times G prime of X, right. Now, actually, I'm going to say, let's capital F prime is equal to F, and consider the expression F composed, consider the expression F of G of X times G prime of X. And let's say I integrate this. Notice that I did not put a derivative on the F. I'm going to use capital F as the derivative. So what is the antiderivative of this expression right here?
Is that F and I don't know what that thing is called, but O, G?
Yes. But we can also say it's composed. F composed G of X, right?
Okay.
But we can also write F of G of X. Right? Okay. So this is the rule that we get corresponding to chain rule. Now, okay. What are some examples of this? Examples. So in the simplest cases, we just recognize being of this form. So let's consider, for example, the integral of 2x divided by x squared plus 1 dx. So does anyone notice how this function can be recognized as something of this form?
It can be arctan.
Not exactly. We're going to use, is it of the form g prime of x times f of g of x? So for example, let's f be one second. Am I doing this example right? Yes, I am doing this example right. G of x. So is okay. Notice, let's look at, for example, g of x, and let's say g of x is equal to x squared plus 1. Then what is g prime of x?
2x.
Okay, let's suppose that f is 1 over x. Then what is f of g of x times g prime of x?
It's 2x over x squared plus 1.
So what we've recognized then is that if we look at this 2x plus 1, then we can rewrite this as being some function composed x squared plus 1 times the derivative of x squared plus 1. So therefore, noticing this recognition, this is equal to, now, okay, I guess we can say what is the, let f of x then is the integral of f of x dx. And that's the integral of 1 over x, right? Dx. And what is that equal to?
Log of x or ln of x.
Log of absolute value of x plus c, right? You know what? I technically made a mistake. I forgot the plus c here. I should write the plus c. Or, okay. So in other words, this is equal to f of g of x plus c, which in our case is the logarithm of the absolute value of x squared plus 1 plus c. Now, this is an annoying way to write it. So let me show you how what the notation is. In general, if we encounter the integral of f of g of x times g prime of x dx, we write, and then I'm going to do this in another color. Let's u and typically one uses the letter u, equal g of x. And then du is going to equal g prime of x dx. So in this notation, I've taken du dx and I've ripped it apart. I've written du as g prime of x dx, and this is purely a piece of notation. So you write this comment, and then you say that's the and then the integral of f of g of x, g prime of x is equal to, well, first off, what is g of x? How can I rewrite g of x? This is equal to the integral of f of what?
U.
U. And then what is, sorry, I forgot the dx here. And what is g prime of x dx equal to?
Du.
Du. Now, suppose that the integral of f of u du is equal to f of u plus c, right? So then we get that this is equal to f of u plus c. And now we rewrite it in terms of g, because u is equal to g of x. So this is a very weird thing. I've ripped this integral apart. So let me show you how you would actually write the solution to this problem on a piece of homework. You start off with the integral of 2x divided by x squared plus 1 dx. And then you write here, I guess, after the integral, you can write in square brackets, let's u is equal to x squared plus 1. Then du is equal to what?
Two x dx.
Exactly. Then after you write the square bracket, you can continue the calculation of the integral. So this continues from this equality. This is sort of a comment. And what is then this integral equal to? How can you rewrite it in terms of u? So what is 2x dx?
Du.
And what is 1 over x squared plus 1?
U.
1 over u, right? Then what is the integral of 1 over u du?
Log of u du.
Almost. Log of what? Remember, it's not the logarithm, it's more generally the logarithm of,
Absolute value of u.
yeah. Then not a du, but plus c. And now if I want to rewrite this in terms of x, then this is equal to the logarithm of what is u equal to?
X squared plus 1.
And so this is how you would write this solution up on your homework. And this is why this technique is called substitution. You are performing a substitution of replacing u with x. So this is how you write this up. So now let's do a bunch more examples of this method. Let me open the window further as the lights gets darker. So let's consider the integral. By the way, does anyone have any questions about this example? So I admit that this notation was pulled out of thin air, and you can make it rigorous, but sort of the fact that we ripped an integral apart, well, this is Calc B. We're not supposed to be rigorous in here. So I think intuitively, this approach is somewhat appealing, right? Then if u is x squared plus 1, then du is 2x dx, then you integrate everything in terms of u, and then you substitute back for x. Okay, let's do another example. Let's consider the integral of sine to the fifth cos x dx. So what am I going to let my u be? I'm going to solve this by substitution.
Cosine of x.
Well, okay. If I let u equal cosine of x, then du is equal to what?
Sine of x.
Negative sine of
Negative
x.
sine of x. Oh, okay.
And now can we rewrite this in terms of, but now look at this. Now this integral, sine x dx, I have a sine to the fifth and I have a cosine to the first power. So that's not directly amenable to actually rewriting in terms of this u. What if instead of cosine, I tried sine? Then what is du? Then it's cosine of x, right? So then what happens if I try not instead of cosine, I try sine? Then what is sine to the fifth?
U to the fifth.
And what is cosine of x dx?
Du.
What's the integral of u to the fifth?
U to the 6 over 6.
Good. Plus c. And now substituting back for u, we get sine to the sixth power of x over 6 plus c. And so this is exactly how you write this problem up on your homework. Okay, doing another easy example. What about the integral of tangents? So how can we rewrite tan? What's the definition of tan?
Professor, I think someone had a question in the chat.
Oh, sure. Can you explain why you did? Okay, you might be a pun. So what is, yes, thanks for telling me about the question. So in general, we have power rule. The integral, the antiderivative of x to the r dx is equal to x to the r plus 1 divided by r plus 1 plus c when r does not equal to -1. And the reason is that if we differentiate this expression, then we obtain x to the r. So this is an example of a power rule. That's the variable of integration. And then there's just power. So I increase the power by 1, and then I divide by the new exponents. And that's what this integrated power rule says. So this is how I integrate powers when the power is not -1. Does that answer your question? Okay, good. So let's move on to the integral of tan x. What's the definition of tan? As a quotient of two trig functions.
Cosine over sine.
No, other way
Oh.
around. Sine over cos.
Yeah.
Remember that sine of 0 is equal to 0, right? So if tan were cosine over sine, then tan of 0 would be undefined. But tan of 0 is defined, so it's sine over cos. Okay, now what should I let my u be?
Sine of x.
Oh, but here's the problem. Then du, if u is equal to sine of x, then du is equal to cosine of x dx, right? But there is no cosine of x dx in this fraction. There's a sine of x dx up top, right?
Oh, okay, okay.
So what should I try instead?
So then cosine x.
Yeah. So in practice, you try one, you'd see that it doesn't work, and then you try the other. And so that's negative sine of x dx. And so I can rewrite this as what in terms of u?
1 over u du.
But notice that there's a minus sign.
Oh,
That's so it's -1 over u du. Right? Because sine x dx is equal to negative du. So sine x dx is negative du, and then 1 over cos x is 1 over u. Okay, this integral we've done several times. So it's negative logarithm of the absolute value of u plus c. And then substituting back, I get negative logarithm of cos x, absolute value, plus c, right? So all of these integrals, these are the simplest type of substitutions. They're the substitutions where you just do one substitution and then you're done. I can give you another example of this, such a substitution. What about dx over x logarithm of x? So what are we going to let our u be?
Can I ask a question about the
Go ahead.
previous one?
Yeah.
Why is it negative sine x dx?
So the derivative of cosine, here, let's write it in green. D cosine of x dx is equal to negative sine of x dx. Sorry, negative sine of x, right?
Okay, thank you.
That's just the basic formula. Sine is the better function to differentiate. The derivative of sine is cosine, but the derivative of cosine is negative sine. So if cos x is equal to u, then du dx is equal to negative sine of x. And so du is negative sine x dx. Good. Okay. Back to the example of x over log x. What should I let my u be?
X over log, I mean, x times log x or x log x.
Let's try that. So what is my du?
Wouldn't it just be dx?
Oh, well, if we're differentiating by this, then we're going to get log x plus x over x dx. So what we get is 1 plus log x dx. Remember, chain rule, sorry, product rule. So we also get this log x factor. And so this doesn't really seem to work, right? Because there is no 1 plus log x inside of this fraction. So let's try something else. Oh, by the way, so here, this is a very good teaching moment. Notice that figuring out what the correct thing is, it's not straightforward. In differentiation, you just recognize that it was a product and you're done. But here you need to figure out which substitution to work, and you need to try several things and figure out what works. So it's not a straightforward process like differentiation. Okay, so x log x didn't work. Let's try something else. And by the way, you don't know. There's no way to know what works. You just have to try several things. Let's try something else.
Dx.
U has to be a function of x. Dx is differential. It's not a function of x.
Could we just try log of x?
Good. What is du?
1 over x.
And look at that. This is great. This is great. How do I, what does my integral look like now? So notice that this is dx over x, right? What's dx over x?
So it would be du.
Over what's log
U.
x?
U.
So it's the same integral that we've seen several times before. This is the logarithm of the absolute value of u plus c, and then we substitute back for x, and we get the logarithm of x plus c with absolute value bars on the outer one. Okay, so this is the end of the easy examples. Now we're going to move on to some trickier examples. All of these examples were pretty direct applications. You need to figure out what substitution to use, but then you were done. Let's do one that requires a bit more cleverness. Let's consider the integral of x over 1 plus x to the 4th dx. My 4 isn't very clear. I'll rewrite that. What should we try for u? Well, let's just try something. If it doesn't work, it doesn't work. Throw a
1
guess.
plus x to the 4th.
Sure, that's a good guess. That's a really good guess to start with. So what is du then? Sorry, 1 plus x to the 4th. Whoops.
4x to the 3rd.
And we don't have 4x to the 3rd dx inside here. Instead, we have x dx. What is x dx equal to? By the way, it is equal to d of what function? What's the antiderivative of x?
X squared over 2.
Right. Now let's forget it, the over 2, and let's instead try u is equal to what?
X dx.
No dx, it's just a function of x. Oh, well, if we try x, then du is equal to dx, right? But then that integral becomes back what we started with, right? Then we just get that this is equal to the integral of u over 1 plus u to the 4th du. So the substitution u equals x never does anything. It just gets us back to where we started, right? But what does this suggest? Using u equals
X dx.
Again, not a function. Well, u equal dx, this has to be a function of x. So dx never comes into u. U equals x doesn't work.
So would we be using the x squared over 2?
Yes. For simplicity, let's just use u equals x squared, not x squared over 2. It doesn't matter. X squared over 2 would also work. So what is du equal to?
2x.
Dx. So when we have du, we have a dx. When we have u, we have no dx, right? Okay. How can we rewrite this integral now? What is x dx equal to?
Half du.
Yeah. So I'm going to take the half out of the integral, and I'm going to get du. And what is 1 plus x to the 4th equal to?
1 plus u squared.
Okay, so our integral did not, but we do know how to integrate this. What is the antiderivative of 1 plus u squared?
That's arc tan.
Arctan. Good job. And now we substitute back. And that's how you do that integral. So this was the first tricky example, because notice in all of these, u appeared as part of the integrand. Here, it doesn't exactly appear, but you have to think a bit outside of the box to do this one. So this is a more tricky example, but this is definitely like the type of things that I'm going to be asking you to do on the homework. So you have to try a few things before you get it. When you realize that it's x squared, this is an aha moment. Any questions about this example? And by the way, one more comment on this example. If you looked at this function right here, why would you suspect that the antiderivative is 1/2 arctan x squared plus c? What you have to do is you have to realize that I'm going to do integration by substitution. You realize it right now because we're doing a sectional integration by substitution. How do you know that you wouldn't try some other technique? In general, later on, you're not going to know what technique to use. But if you try substitution, you try a few things and they don't work, but you have to hit on this substitution. And then when you get on this substitution, the problem yields itself and you get the answer. Okay, here I'm going to do a more interesting example. This one is going to be the hardest example, one of the hardest examples that we consider today. The integral of the square root of 1 plus e to the x dx. Okay, what are we going to try? Let's u okay, what is one? Okay, there are two things that I think are clear to try. One of them doesn't work, the other one works. Just guess.
1 plus e to the x.
Okay, so I think that's the most obvious first thing to start off with. Let's see if this works. So du is equal to e to the x, right? Dx. Let's see if this works. Then here, well, the problem is we don't have e to the x, but I guess we can. Let's try this. Then if u is 1 plus e to the x, then e to the x is equal to u minus 1, right? So I guess we can rewrite this as we'd like to have e to the x dx in order to get a du. But then as a result, we have to have the integral of 1 plus e to the x divided by e to the x, right? And how can we rewrite this? We can rewrite this as the integral of what?
U over du.
The square root of u, right?
Oh, okay.
And then what is e to the x?
Du over dx.
E to the x is well, no. E to the x dx is du. But what is e to the x? We rearranged it in here in terms of u.
Oh, u minus 1.
So this substitution brings you over to here. And at this point, you're sort of stuck. You know what? maybe the integral can be solved this way. So this isn't the substitution that I had in mind, but let's just try and see if we can solve it. So let's W equal what? So now we're going to try and do a second substitution.
U minus 1.
Okay, so that's not going to work. I know from experience. I guess, okay, that doesn't do much to resolve the square root of x. We're just going to get sort of back to where we started. It's not going to make much of a difference. So you can try and see why this doesn't work. Let's try another substitution.
Root x?
Yeah, I think that's, so by the way, I don't know if this is going to work, root u. So dw is equal to 1 over 2 root u du. And then if we actually rearrange this, then w squared is equal to u, right? We have this equation, right? So if we were to rewrite this integral in terms of w, this would be, so we want to have 1 over 2 root u dw. Sorry, 1 over 2 root u du. So we could rewrite this as 1 over 2 root u du. Then to compromise, we have to have 2, and then root u times root u is u, divided by u plus 1, u minus 1, right? By the way, how can I rewrite this integral right here? 2u divided by u minus 1 is equal to what? I can simplify this actually.
U minus 1.
Not exactly. So 2 to the u over u minus 1. I can write this as 2 to the u minus 1 plus 2, right? Over u minus 1. And then what does that simplify to?
Four.
Well, 2 divided by u minus 1 is equal to 2 times u minus 1 divided by u minus 1 is 2 plus what? Two divided by u minus 1, right?
Is it 2 to the u power or 2u?
That's 2 times u.
Okay.
Right? Why did I have 2 times u? Because I want to have square root. I know that dw is 1 over 2 root u du. So I'd like to group this term together. So then I look at this expression and I divide it by 2u, so I need to multiply by 2 square root u. And I had a square root u here, and so that becomes a u, right? So I'd like to make the substitution dw. So I'd like to group this term to one side. So this is equal to this. You can just compare these two equations and they're equal, right? 2 divided by 2 is 1, and u divided by square root of u is square root of u. So we're good, right? And so we can write this as 2 plus 2 divided by u minus 1. Du, times 1 over 2 root u du. And so this becomes 2 is just 2. what is, remember that u is equal to w squared. So what is 2 divided by u minus 1 in terms of w? So u is square root, w is square root u, so w squared is u. So u minus 1 is what?
E to the x.
No,
Yes.
w squared minus 1. Right? And what is 1 over 2 root u du? What is that equal to?
DW.
Yeah. Let's me check the chat. Well, we already have the 2 in there, so it's just dw. Okay, so now we're solving this integral. Well, we can make some progress because the integral of 2 dw we just know. Now, what about the integral of 2 divided by w minus 1 dw? Well, here comes a really clever trick. So I'm going to tell you about this later, but let's consider the expression 1 divided by w minus 1 plus 1 divided by w plus 1. So how can I rewrite that? Actually, you know what? I'm going to be clever for a random reason. I'm going to write minus. So how can I combine these fractions into one?
Multiply by the greatest common denominator.
So I can write w plus 1 divided by what? What's the common denominator here? W minus 1 times w plus 1 is what?
W squared minus 1.
Right? And then the second factor is w minus 1 divided by w squared minus 1, right? So let's see what happens. The w's cancel and I get 2 over w squared minus 1. Whoops. So in other words, I can rewrite this as the integral of 2 plus 1 over w minus 1 minus 1 over w plus 1 dw. And we can integrate each one of these individually. What is the integral of 2?
2x.
2w. Now we're going to do 2 steps in one. Technically, you could do a substitution w minus 1. The integral of 1 over w is logarithm of w, right? What do you think the integral of 1 over w minus 1 is? So let's try to do this integration by inspection. What happens? Okay, go ahead.
Log absolute value of w minus 1.
Yeah. So if we look at the derivative of this, then it's exactly 1 over w minus 1. So we get log absolute value of w minus 1. And what do we get for this one? So I should say.
Same thing, but with plus.
Yeah. Oh my God, we finally got an answer. Now let's substitute in terms of u. So what was u in terms of w? So w was equal to the square root of u. Sorry, I want to rewrite this in terms of square root of u. Now, what was u equal to in terms of x? U was 1 plus e to the x dx, right? So I can write this as 2 square root 1 plus e to the x plus logarithm square root of 1 plus e to the x minus 1 minus the logarithm of the square root of 1 plus e to the x plus 1 plus c. And so this example is supposed to illustrate that sometimes integration is very hard and you just have to be very perseverant. By the way, let me tell you what an easier way to solve this problem was. If instead we did u is equal to the square root of 1 plus e to the x, then we would not have to do the second substitution. In other words, we do both substitutions at once, right? Because our second substitution was the square root of x, and our first substitution was 1 plus e to the x. So we could do both of those substitutions at the same time if we instead started with this substitution. And you can see then that if you sometimes choose the wrong one, it's still possible to do the answer, but the work becomes longer. And this was a pretty long process to solve this integral. This integral didn't want to yield. It really kept on fighting. And yeah, so here is an example of an extended calculation. Now, what was the most non-trivial part of this calculation? There was one thing that you had to pull out of complete thin air. And what was that?
That was the log part.
The log part was sort of standard. I think the most non-trivial part was this decomposition right here. Where did I pull this out of, right? This was surprising. And in general, we're going to see that this is part of partial fractions. There is going to be an idea of partial fractions. And this is going to be there's going to be an integration technique of partial fractions. And so that's where this comes in. Oh, so I have 3 minutes left in class, so I'm not going to do any more example. But at the end of class, we ended with one example that was pretty extended. And I think it's very good that we did this example because it shows you that integration is hard. Integrating is not an easy process. It's not like derivatives where you just recognize the function and you apply the rules. You have to be creative. And I think this is a really creative step. So yeah, sometimes you just keep having to work, keep having to do substitution at one substitution after the other. And it's not all as easy as the first examples of substitution where we just had literally 2x divided by x squared plus 1. Well, the numerator is the derivative of the denominator, so we just generally get this. Here, it didn't want to yield. We just kept substituting, right? So I think then what we learned about substitution is the general way to write a substitution is to write in square brackets what your substitution is, then what your du is, and then rewrite everything in terms of du, then solve the integral, and then substitute back. So that's the main lesson about integration by substitution. That's the technique. And on the assignments, which I'm going to post today before midnight, I'm going to have a bunch of integrals by substitution. I'm not going to tell you which ones are by substitution, because tomorrow we're going to learn about several more techniques. So tomorrow I will do integration by parts and partial fractions, which is the technique that we use here. And if I have time, maybe I'll talk about trig substitutions as well. So trig substitutions are the super deviously clever ones. Trig substitutions are the most occult black magic part of integration, because it really feels like you're pulling them out of thin air. You have to know that you have to do these tricks. They're the most trickiest of tricks. Okay, any questions?
So should we wait until after the lecture on Thursday to really start the homework, or should we?
No, I'm going to post the homework tonight before midnight. And then some of those problems are going to be substitution problems. So you're going to be able to solve half of the problems on the homework. I guess it might be a bit dissatisfying to not know which one of the problems you can solve at this moment, but you can try some of them. with the caveat that I'm going to tell you that half of the problems you're not able to solve at this point.
Is it split in the way we learn it? So like we won't be able to do the second half, or is it just split among it?
I haven't written the assignment yet. I was going to write it right now. So I will send you you know what? I'm going to send you an email telling you which ones you can do. Maybe. I will write the assignment and then I will decide. So I have not written the assignment yet. I've been busy. But I also decided that I didn't want to write the assignment until after the lecture, because if I had written the assignment after the lecture last week, it would have been a different assignment, because I knew that I had to adjust what I was doing, because I was too formal at the start of the course, and my assignment was sort of formal as well. Right now, this assignment is just going to be computation. This is computation, right? Everyone agrees that this is computation. We're doing computations now, right?
Yeah.
Right. So now this is calculus. This is what you're supposed to be doing in calculus B. In calculus B, you're supposed to be doing a lot of computations. This is computations. These are what B computations look like. Right. Then this assignment is going to be the assignment that you should be given. This is going to be a very standard calculus B assignment. You're going to have to compute a bunch of integrals. And you are not allowed to look up these integrals on the internet. Unfortunately, it is incredibly easy to look up integrals on the internet. You should resist this temptation. So please do not use the internet to look up integrals. It is too easy to look up integrals on the internet. No looking up assignment problems on the internet. So you would not even go to check for this. There are services that automatically compute the integrals. A computer computes them for you. So something like Wolfram Alpha, you can just type in the integral and it'll give you the answer. And you are not to use Wolfram Alpha for this assignment. Now, it's sort of stupid because I'm giving an assignment with integrals and computers can do integrals. So that's unfortunate. When I was an undergrad, I took Calculus 1. And Calculus 1 involves a lot of derivatives. There was not a single question on an assignment which asks you to compute a derivative, because computers can compute derivatives. And so the assignment was made to be an assignment which computers could not solve. Now, that was because it was a theoretical course and you had to do a lot of proofs. Similarly, I could give you an assignment which I could teach this course in a very theoretical way in which none of the questions explicitly ask you to compute integrals. But that's not what I'm supposed to be doing. I'm supposed to be asking you to do computations. So there's a caveat that a computer can do this computation, but you're not going to use a computer to solve them. You're going to learn how to do it yourself, right? Otherwise, I'm going to make the midterm exam a 2-hour exam and proctor it. I would rather do a take home. So please do not cheat on this assignment. Try and solve the integrals yourself. I'll send you an email with more information. But so today we introduced a bunch of computational methods for solving integrals. And that's going to be the rest of the course. We're just going to keep computing integrals. Sounds good?
Yep.
Okay. See you on Thursday. And I'll send you an email with some updates once I post the assignment.
Thank you so much.
No worries. See you.